Hello. So, hello everyone. I am joined by the wonderful Andre. Um, we'll start with some introductions. So I'm Natan, maths teacher, contributor on helekmaths.com. Love maths, love thinking about it, love talking about it, love teaching it. It's the dream. Um, Andre and I went to secondary school together, have grown up together. It's wonderful to be able to do this with you. Andre, do you want to give a little intro into who you are and why we are talking today?
Yep. Hi everyone. My name is Dr. André Shamsabadi, and I am at the moment, a COVID-19 diagnostic researcher. And we are talking today because Nathan made a video yesterday explaining some of the maths that could be involved around doing COVID diagnostic testing, especially in a point of care setting such as a school. And he asked me to consult really quickly on the maths behind the video. And we're here to do a sort of review and discussion on what he made in the content in the original video.
Yes, thank you. Yeah, and I think that's a very kind way for saying we tore it apart, basically. So I, because we are going to have maths testing in schools over the next few weeks, and as a math teacher, this is obviously something I'm interested in. And in particular, we had a conversation on one of my WhatsApp groups, my school WhatsApp groups, about the sensitivity of the test that we're going to do, where one of the people in the leadership team was saying, oh, these tests are 60% effective. And there were rumours that someone said that if you do two of the tests, it becomes 120% effective. And you can imagine that the math department was not having any of that, basically. But the question was asked, well, what is the sensitivity rate if you do two tests instead of one? Surely it's better to do two instead of one. And so I tried to think about that, and I spent a lot of time when I should have been asleep, thinking about it, and making a PowerPoint about it, and thought, oh, this is such an interesting thing to make a video about, especially because it felt like math that's so easy to have misconceptions around. And it turns out I was right, because I had all the misconceptions, all of them. So what we're going to do is look through the PowerPoint together that I put together, and basically just talk about what is true and what is fundamentally COVID misinformation. Because we've discovered that it's very easy to create COVID misinformation, even when you're trying to do good. And actually, kind of because I was trying to do good, I've created the most evil kind of misinformation, because it's so believable. It's so believable.
Yeah, completely. And I think it's good if we can sort of round off some of the misconceptions now so that people don't make the same mistakes in the future, and people get an appreciation of how not as straightforward as some of the numbers can be applied in a
No.
sense.
And also how much we've been living in this pandemic for like 9 months, and yet we still don't, like, the normal people of the world, me, still a math teacher, still do not understand the most fundamental things that I've read on the news every day, which is sensitivity of testing, which I thought I got, I didn't get. So we're gonna share the PowerPoint. I'm gonna share the PowerPoint. So this is what we were looking at. This is the PowerPoint. Do you want to quickly explain what a lateral flow test is?
Yeah, I can actually get a diagram up for the lateral flow test if that helps.
Yes. So do you want to share?
Here we are, and that's
Cool.
nice, and that looks nice and visible.
It
So
does.
this is one of the standard image that you can get up if you type into Google Images lateral flow tests. But I'm here to explain all of the sort of like surrounding science and why certain maths numbers will bring about from one of these. So this is something that a lateral flow test shouldn't be anything that's completely new to anyone, because it is the standard test that is done in pregnancy tests, like the standard pregnancy test, which is a urine dipstick, which is encased in a small plastic device, is a lateral flow test. And the way it works is split into 4 sections. So the first section, as you can see on the left here, is the sample pad. And the job of the sample pad is to absorb the whatever matrix, whatever sample is provided by the patient. In a pregnancy test, this is urine, but it could be reserved for any bodily fluid, such as blood, such as saliva, such as a nasal swab. And effectively, this is a porous piece of material that acts like a sponge. Its job is to wick all the excess bodily fluid and store it into the device. And the way that the device works is that the sample then flows through the strip, as you can see through the arrow with the direction of flow, and it moves via capillary action through the pores of this porous material. And the second part that we reach is the conjugate pad. And the conjugate pad is arguably the most important part of the lateral flow device, because this is where you house your reporter probe, which is typically binded to your binding agent, which is in 99% of cases an antibody. So what you would have is an antibody which specifically targets a bit of the virus, so the bit of COVID-19 that you want to detect. In this case, let's say you want to detect the spike of COVID-19, because I think that visually that is what people are most familiar with when you come to think about the visuals of the actual virus. So let's say you have an antibody which is very, very good at sticking onto the spike protein of the virus. Mm-hmm. So what that does is if you provide a sample which does in fact have COVID, you will be getting a lot of these antibodies attaching onto the spike within that sample. And these antibodies, as you can see with these purple circles, are attached to what is called a reporter probe. And all this does is that it gives about a signal. The whole job of these purple circles, the reporter probe, is to just give a signal. And in these pregnancy tests, these normally just produce a red signal, which you can see as a red line. So once you have your virus attached to these reporter probes via the antibodies, it then flows through the strip and reaches the test line. And the test line will have another set of antibodies which do the exact same job. It attaches to the protein of your choice. In this case, let's say again, the spike protein. And what you end up having is forming a sort of sandwich where you have a row of antibodies on your test, which is sandwiching the spike protein, which is then connected once again to your antibody conjugate to your reporter probe, and then the reporter probe produces a nice red signal on your test line.
How does it do that?
What do you mean?
Like, where does this red signal come from?
The red signal is inherent part of the probe. It's like a red bead almost.
Ah, okay.
If you didn't have COVID, there would be no sandwich to form, and the reporter signal would just flow right through, and it would
all
not
the way to the way.
stop.
It wouldn't be grabbed by this test line.
Exactly. It wouldn't be immobilized on the line. It would just flow straight through to be picked up by the wick, and the wick is not visible. So when you look at any of these lateral flow devices, you can only see the area here. Like
that's where the test results oval is above it.
Yeah. Everything to the left and to the right is not visible.
So how come the test line has shown up in the non-pregnant bit?
The test line will never show up. What you see is the control line. The control line is always visible, and the control line tells you that the test has worked properly.
Oh, because something has passed through it.
Yes, exactly. So the control line is designed to pick up reporter probes no matter what. And the way it does that is that it detects something that's very common in humans, like a human protein inside your sample.
Oh, so that's really interesting. So if you look at the pregnancy test, when it says not pregnant, the one line it represents is like the second one, which is the control line.
It is the control line.
Okay.
Yeah. And when you are pregnant, that is the control and the test line you see.
And so if you have COVID, you will see the control line and the test line show up, because the test line has detected the reporter.
Exactly. Whatever virus protein of interest, yeah, and it's picked up the reporter probe, which you've immobilized onto the test line.
Ah, so it's basically attaching to something, and then if you have COVID, it's getting caught in a net, and if you don't have COVID, then it's just going through the net. Either way, it goes to the control line. The control line just is like, okay, this is from a human, so we can say it's worked. Then it goes through to the wick. Exactly.
Yeah, the control line says that you did in fact have flow, so that you can guarantee that your probes have been released from the conjugate pad. And they are designed to detect human proteins as well. So, well, typically they're designed to detect human proteins so that you know that the test was done properly.
Is the test line saying, oh, there's virus bits here, or is it basically saying, oh, we found the antibodies, that means that the antibodies have attached themselves to the virus?
Well, it could be whatever you want. You can detect whatever you want. So you can design it so that it can detect antibodies against the virus in your sample. What I think is more useful, at least for testing it in the school setting, would be testing for the actual virus itself. Testing for antibodies would be useful for, let's say, people who have been immunized to see the level of antibodies within a person's system. But if you want to know if someone was infectious, it'll be more useful to see the actual virus. It all depends on what antibodies you're using. You can develop antibodies to target almost any human protein.
So before we go into what maths we ended up doing with this, what might be the things that could go wrong with these tests? Why do they not work every single time?
Okay, so the reason I work every single time is purely because you need bits of the virus to immobilize the the reporter probe onto the test line. Like, that needs to happen. And the level of intensity is directly correlated to how much of the virus you're presenting.
So the more virus you are presenting, the more likely that the conjugate pad will release these reporter probes to go up the line.
Well, the reporter probes are always being released, but the amount that are being immobilized on the test line is directly correlated to how much virus or virus target that's present in the sample. For example, if you have 0, you'll get nothing on the test line, which is what you want, because you want the test to stay negative when you have no virus.
Yeah, you want nothing to show up when you don't have the virus.
Yeah, but there is the gray area, which we'll get into a lot in the next couple of minutes, where you do in fact have the virus, but you just simply don't display enough to attach enough reporter probe onto the test line to get a signal.
Okay, so we're going to hold on to that thought, which is what happens if you don't have enough of the virus in your system to get picked up, and we're going to think about this idea of sensitivity based around that a little bit later. So, going back to the PowerPoint, this is the PowerPoint that I made so that I could record a video about it, talking about lateral flow tests in school. These are just headlines about the mass testing that was going to happen. So, if we work through this, the first thing that I talked about is just this comes from the government handbook that they basically created this like PDF handbook for teachers in schools, mainly for head teachers, I think, at this point, about an introduction to rapid asymptomatic testing for school and colleges. So it's in general testing everyone, including asymptomatic people. You might have heard about the trials they did in Liverpool, for example, where they did just mass asymptomatic testing, and they did a lot for university students coming home as well. And we'll talk a bit about some of those results later. But the key things is that pupils and students, not sure why there's a distinction there, but still, offered 2 lateral flow device rapid tests spaced 3 to 5 days apart, minimum 3 days. And at first, when I first looked at it, I was like, why minimum 3 days? But now, having had our conversation in the past, we will talk about why minimum 3 days is a good thing. The workforce, teachers, people that work in schools, offered 1 test in the first week and weekly thereafter. These are simple to use, result in 30 minutes, which we can see because if you just put the liquid on the pad, it goes up the thing and it takes about, you say, 30 minutes to work its way up that membrane.
Yep.
Yeah, it's like those old experiments where you put a flower in some like coloured liquid, and then you see how long it takes the petals to change colour. Where it's just
precisely
going up the membrane.
30 minutes is just the operating time of the test, exactly.
Cool. Okay, so the key thing that we want to talk about, how sensitive, how likely these lateral flow tests to pick up a positive case. Because that's the important thing. How likely is it to actually, especially in some asymptomatic cases, how likely is it to actually pick it up? The key thing is that there are 3 different people, in my eyes what I saw, there are 3 different people that might be doing these tests. Lab scientists, healthcare workers, trained healthcare workers, and self-trained members of the community. And I've put my face there because I am one of those, or might be one of those self-trained members of the community, not a healthcare, not a lab scientist, just a person administering these tests. And actually, these tests in schools are going to be self-administered by the students. So they are very much self-trained members of the community. And the percentages that you can see underneath, you can see here, they match up to how sensitive, according to the government data, how sensitive the lateral flow test will be using is. So it's for a lab scientist, 79% if they did it, healthcare worker, 73%, but for a self-trained member of the public, apparently the sensitivity is only 58%. So the diagram I showed over here is that for 100 positive cases, where each one of these circles is a positive case, it will pick up 58 of them, but it will miss 42 of them. 42 out of 100 of these positive cases. Now, this is our first, is this true moment?
Yes, this is true, but I think you do have to understand a little bit of how these numbers come about, because a test doesn't magically become less sensitive in its ability to pick up COVID based on if I'm running the test based off you're running the test. So I think the big question that people might be asking initially is, why are these numbers different? Like, why are they different at all?
So
Rather,
why might they be different at all?
so the way they're different is that these numbers are numbers that the government, or not the government per se, but the developers of these tests would have found to be the sensitivity, which we'll get into in a moment, of the test when it's administered, as you said, by the people running said test. But they'll be using the exact same test to get these numbers. And the reason these numbers are different is because they have a different success rate depending on who's performing it. There's nothing wrong with it. There's nothing changing fundamentally about the test itself, but the success rate when said person described in the picture here is running the test on someone who is COVID positive.
And success in this case is picking up that positive case.
Exactly, picking up that true positive. So picking up the positive case when someone indeed has COVID. You show there at the bottom that's the case of a negative when someone has got positive. So like the false positive result is basically 0, which remains exactly the same.
The word specificity down at the bottom here, which you might hear, the specificity of test is basically how likely. So here it says 99.68%, and that means it's basically never going to give you a false positive. It's never going to find COVID when there's not COVID, and that kind of makes sense with what your diagram of the lateral flow test. If COVID isn't showing up on that test line, why would that test line show up?
Yeah, exactly. Well, there are various reasons why it could, but they're very, very rare and far between, which is why the number for specificity is so high. So you have to, when people develop these tests, they understand that a lot of the people doing them will be symptomatic. If you are symptomatic, you're likely to be sent one of these tests or to want to conduct one of these tests to see if it's COVID. And if you're symptomatic, you are very likely to just be displaying proteins of a foreign virus in your system. And I mean, SARS-CoV-1 was a thing as well. So that is a sort of like that's a relative of SARS-CoV-2. And you want your test to not only detect COVID, but not detect SARS-CoV-1. So the antibodies developed are specific just for only detecting the COVID protein. But they're not
SARS-CoV-1, that was just SARS. Like people just know that as SARS.
That was SARS. So
I messed with your flow.
Not to worry. But yeah, so because people taking these tests are likely to be viral in some sort of sense, because I mean, if we just think about symptomatic patients, you want your test to detect COVID, but absolutely nothing else. And antibodies, while being incredible at doing so, are not 100% foolproof, which you can see here in the specificity. Like, you basically will never get a true, these false positive results. But given a big enough sample size, like 99.68%, if you are reporting 10,000 people,
that'd be 32.
You would expect to see a very small amount of false positives.
Okay, exactly. Yeah, but we can, at least for now, ignore the false positive thing, because although in a school, a sample of let's say 2,000 people, you might get 1 or 2 false positives. But also, I would say false positives are not that bad, because all it's going to do is make someone self-isolate. And actually, in these cases, what the government says is if you get a positive in these lateral flow tests at school, you then need to take a PCR test, which is the one where you go to a test site, the full shebang, goes to a lab, anyway, to back that up. So they really are discounting false positives. So we are basically going to discount false positives, which is good.
Yeah, I mean, fundamentally, it's a bit of a non-issue because false positives are a lot less troublesome to us than a false negative.
So why would the self-trained member of the community have a 58%, but the lab scientist a 79%?
Fundamentally, it will come down to operator error. I mean, the only difference in the actual test when you're testing a patient sample is the member of the person administrating the test. So the average person, say people and or students, as the government likes to place it, would just fundamentally not either provide enough sample, not administrate the sample into the test correctly. There could be like spillage. There could not run the test for the correct amount of time before collecting the results. They might misinterpret the results. If the test line is a bit faded, then due to a somewhat grey amount of virus present in the sample, then it can go either way if someone sees that as a positive or as a negative. It can come down to eyesight, and fundamentally that is going to be where this 21% discrepancy in sensitivity comes from.
So I know that what I assume something very similar, that it's just down to users not getting enough of the virus on the swab or something. And
exactly.
But the key thing that we're saying here is that, look, if there's 100 people all with COVID and they're swabbed by me or by themselves and they're just random members of the community, 58% should mean it picks up 58 out of the 100 things on average.
Yeah.
On average, in a big enough sample size.
Yeah.
Okay. So far, so good. We advance onwards. So the next thought process was, okay, in a school. So we have our friend Lucas here. He's showing up to school, doesn't realize he has COVID, asymptomatically has COVID, so no symptoms. But school's doing mass testing. What could happen? So this is just talking about the probability again. There are two options on this tree diagram. Either he gets a positive test. Remember, he has COVID. The positive test will happen 60% of the time. The negative test will happen 40% of the time. And so for 100 people with COVID, we get 60 true positives, so 60 people that are correctly told they have COVID, but 40 people with a false negative who are incorrectly told they don't have COVID. And then we were talking about how bad a false negative is, and I think in a school setting it's particularly bad because let's say you have kids who aren't that safety focused anyway because they think, oh, it's not going to affect me badly anyway, and then you give them a negative test result, well then why would they follow any of the rules that you've just told them they don't have COVID, even though allegedly 40% of the people with COVID doing this test are not going to be told they have COVID.
Yeah, completely agree.
But this is where the thinking starts to get a little bit wrong, because I assumed, this is the key thing, I assumed that the 60% was random. That the 60% is generally random. It's just, the test has a 60% chance of picking up the virus. It's not linked to anything. It's just 60% chance it just picks up 6 out of 10 of the virus, and that's it. But that is absolutely
which is
not the case.
Yeah, I mean, that is not an irrational conclusion to come to because that feels like what the number is telling you. It feels like the classic case of Lucas has got 100 balls in a bag and 60 are blue and 40 are red. And what's the possibility he picks one up that is blue? Well, in reality, that is not quite the case, which I think we'll get to in the next couple of slides.
Yes. So the next slide is where things start to go wrong, because the idea that we were talking about on a school WhatsApp chat and in general is, well, if one test is 60% effective, what about 2 tests? What about 2 tests? What if I just, instead of doing 1, I do 2? And for this case, let's say 2 back to back, like literally 2 next to each other. So Andre's example with balls in a bag, well, if I pull out a blue ball and I then immediately pull out another one, I have a higher probability that one of them was a blue because I've done it twice. If you roll a dice and you roll a dice twice and you want to get a 6, rolling it twice will give you a higher probability of getting at least 1 6 because you have 2 chances to get a 6. So I assumed it was similar. Well, there's just 2 chances for the lateral flow test to pick up this virus. And so the idea was that, look, what's the probability? 60, 120, 92, and 84. And I said the answer was 84%. We'll see why. I think, is the answer actually 60%?
Yeah.
So this is
I would say the answer is, I think the answer is still 60% or very close to 60%. If the number does move, it will be still very close to 60%.
So this is the key thing.
Yeah.
We'll talk about, we'll go through the misconception on the next page first, and then we'll talk about why it's actually 60 and not 84. Firstly, it's definitely not 120. You can't just add 2 probabilities together, because it's like if you flip a coin, probability of getting heads is a half, and then if you do it again, probability of heads is a half, but 2 heads is not half plus a half, which is 1. Because that's like saying 3 heads would be half plus a half plus a half, which is 150%. But probability works from 0% to 100%. You can never have probability above 100%. This is just very wrong. I'm going to straight up go. It leaves. 92% was just an irrelevance, just a classic multiple choice, add in another number that's a bit weird. So these are our two main options, and I'm going to explain the misconception as to why it's 84%. So, 2 lateral flow tests. If you assume they are random, which they are not, although I did assume they are random, what happens is there are 4 options. Either you got positive positive, positive negative, negative positive, or negative negative. And in this case, the probability of getting those things is you just multiply the 2 probabilities. So for 2 positive tests, it was 6/10 times 6/10, which was 36 out of 100, 36%. Down here, the negative negative was 16%, 4/10 times 4/10. And in the top 3 scenarios, you get at least 1 positive test. And remember, we said that because it's so specific, if you get a positive test, you almost definitely have COVID. Andre, it's running out of time.
Oh. That's frustrating.
That is frustrating.
How are we going to fix this?
We'll just finish it up in... we'll just do part 1 and part 2.
Okay, you can splice the videos.
Yeah, it's chill. And also, it's fine, because this part can be talking about the misconception, and the second part we can be dealing with the truth.
Mm-hmm.
So that's chill. Okay, so we are dealing with the misconception. So, what you can see here is in these 3 scenarios, in 84% of the time, so 36 plus 24 plus 24, the 84% of the time, you're getting at least 1 positive test. So the lateral flow test has done its job. It has found positive tests, found positives when you have COVID, success. But in 16% of the cases, so down here, you are still getting a false negative. So still 16 out of 100 people are told twice they have a negative test, so we're definitely going to think they have a negative test, even though they do have COVID. All seems pretty legit.
Yeah.
All seems pretty legit. I found it legit. When I said it to people, they found it legit. But we are having a key misconception about what sensitivity of tests mean. The sensitivity of a test, that 60%, is not random. It's not just randomly 6 out of 10 is going to be like that. It is in fact something different. And what we're going to do in the next part of this video, because we're running out of time for our Zoom meeting, the next 5 videos, we're going to talk about what does sensitivity actually mean in this case, and why with 2 lateral flow tests is it going to give you the exact same sensitivity if you do it one after the other. Does that make sense?
Yeah.
Cool. Okay, dreams. Okay, thank you very much for listening to part 1. In part 2, which is going to be in another video, we're going to be talking very specifically about what does the sensitivity in these tests mean, why are they not random, and why when you do 2 lateral flow tests back to back, actually the probability of you getting the result you are looking for is exactly the same. So see you in the next video.